other. And in consequence, we're generating any products, so either aggregates on the right side or crystals on the left side, which are also, because of size and weight, exceeding solubility limit. The crystals have the disadvantage that we're normally using to homogeneity purified proteins. On the right side, we just have the aggregates, which in the end is not to homogeneity purified proteins, it's just technical grade. As long as we have foreign proteins accompanying here in the aggregate, which are not catalytically active in view of our compounds or any side products, then this is the cheaper, easier way. Then we do have the containment, and we differentiate gel entrapment and membrane retention. Gel entrapment means like we are containing the proteins in a gel. For sure, we do have a significant diffusion limitation here, but it's very sturdy, and these gels are softer, so the carriers, what we have up here, front row, top row, they're rather breaking, or there's a chance that they are breaking if we have a very this is not true with gel entrapment. However, it's hard to pack them into continuously operated clumps. Yeah, and then for sure we still have the membrane retention, and membrane retention from my point of view is no immunization. That depends on in which lecture book you take a look at. Membrane retention is directing homogeneously solubilized proteins which are filtered via a membrane being retained. Yeah, and that's where we stopped last time. That was introduction of ionotropic gelation. So where we have, for example, one for glucuronic acid or one for mannuronic acid. The difference that are being used here in the immobilization is the amount of the cations being added. So these oligosaccharides or polysaccharides do have a sodium connected, coordinated to the carboxylate function. Now, if we add calcium, which is a divalent cation, in contrast to sodium, which is a monovalent ion, so we add a bridge, a linker, which is linking two negatively charged carboxylic acids. And so linking the strings, and if with a calcium solution we still add our protein, or we have already the protein together with the polysaccharide solution and drop in calcium ions, then we get, in view of the droplet size, that we drop in there small gels. So that's ionotropic gelation. I showed you some pictures last time. The other alternative in view of entrapment is most often used as ion-ion interaction, so that's adsorption or weak interfaces. And this making use of that proteins have a surface charge. Different proteins have different surface charges, absolutely, as well as in view of positive or negative. And depending on the surface charge of the protein being the target, you choose the resin, and often cation exchangers are being cation or anion, so ion exchangers are being used because they have the opposite charge, and so you can easily coordinate. A very typical one being used, which comes from downstream processing and fine chemistry, that's DAE, cellulose. So cellulose is the backbone here, and DEA, that's the amine positively charged surface components. Then we're moving on to covalent immobilization. And by the way, these immobilization methods I demonstrate to you here right now, you do not need to know by heart for the examination. However, what you need to know for the examination are the methods how you characterize, so the reaction engineering points that we will discuss in a moment. So a very typical immobilization surface, because it's pretty inert, either going to an aqueous phase, but also at the same time going to an organic phase, is glass. However, glass, if you look out your window, is very sturdy, it's not functionalized, therefore we have not much dirt attaching to the window. Even sometimes you can't look out, but that's a different story. And so we need to modify the surface of the glass to enable fixation of an enzyme. And in the covalent immunization methods, we normally make use of the amino function, amino residue in a protein. And now, if you remember, the proteins are set up out of amino acids. So we always have a function of amino and the acid. And so just before we made use of the carboxylate end of the peptide made out of amino acids. And now for the covalent immunization, we're making use of the amino end. And by the way, short detour, proteins are in part set up of peptides. Remember, what you should also do in view of a principle is the difference in peptide synthesis, thermodynamic, and kinetic control. If these words don't trigger anything in your brain, look at the class on the lecture on hydrolases where we discussed peptides. Okay, back to the story. So on the glass surface, we have a hydroxy function. Glass is silicon O2, and endpoint. Sometimes we have hydroxy functions, and now there's a special chemical, xenane, being used where also lithium compound is in there at the end. It has also an amino function like the protein, and by a harsh chemical reaction, so this surface is modified that we have the silicon chain on top of the surface. So that we're ending up in the end with a situation where the modified glass surface and we've changed our hydroxy function to our amino function. Then we have the amino function of the protein. So we have two amino functions we would like to covalently combine, fix. And this we're doing with a chemical which is named glutadialdehyde, what you can see here. So it's a 5-carbon chain. 3 methylene function in the middle, and at the endpoints we do have aldehydes left and right. And aldehyde in a very soft manner, or meaning under ambient reaction conditions, close to room temperature, no extreme pH, we do have a reaction forming a non-hydrolyzable bond, and that's named the Schiff base. So by this means, we are attaching the protein to the surface via 2 amino functions, where we end up with a linker that is not hydrolyzable by water. Alternative could have been, and there's some even out there, that we would bind the amino function to an acid function on the surface, what we don't have in this case, but then we would end up with an ester. And the ester, as you already know also from the hydrolyze section, could be cleaved by water and would not be stable. Therefore, here the aim is to set up a link where the linker produces a link that is not hydrolyzable by water. Okay, here you can see this one again. Trisoperl, that's just a commercial carrier where you don't need to do this step beforehand. So you just buy a glass carrier with the amino function on top. Then you add the glutadialdehyde, the protein, same story as before. These commercial products of the immunization matrices, they differentiate in this backbone. So they do not really differentiate in the surface, they're differentiating in the backbone. And the backbone is differentiated in size, volume of the individual particle, and at the same time of the porosity. So porosity in terms of how many pores, how wide the pores are, or how small, these are topics or characteristics where you can select from. Yeah. Then what you see here is immobilization of on a different cation exchange resin. That is amberlite, also like the AE cellulose, a very typical ion exchanger, a cation exchanger. And on the surface, we do have carboxylic acid esters. However, here you see what I just mentioned. You can also immobilize here with a diamine form an amide bond, then you have a free amino function to the outside, then you go on this with a glutadialdehyde. So the same one described here. And then you have an aldehyde on the outside and you add your protein with the amino function. Meaning you're ending up with two shift bases to have a clear covalent linkage, but the weak point is that the linkage to the backbone is an amide. And this amide you can hydrolyze at very acidic or alkaline conditions once again. Yeah, and a very prominent backbone also, last one, I would like to introduce to you. That is Eupergit. Eupergit is also like super commercial carrier that's out there. It's made up out of two chemicals you see up here. This is the whole backbone what you buy. So you have some imide functions, and you have, that's now a different technique. You have an oxyrane or an epoxy, so a three-membered ring with an oxygen in one corner, which is the functional group where you attach to. Before we have an ether, and the ether is totally stable, so you cannot hydrolyze it. But with the amount of the free amides, you can change surface polarity and charge, which might also affect the catalysis. The immobilization, however, is not making use of glutadialdehyde, forming a shift base as discussed before. Here we have a direct reaction of the amino function with the oxyrane, what you see here. And this forms, once again, a very stable, non-cleavable, non-hydrolyzable linkage. Advantage of this method is that you do not need an extra chemical like glutadialdehyde, so the protein will directly attach to this oxyrane. Yeah, these are the fundamental methods that they are out there in view of immobilization of proteins. And now we are in the following, we're talking for one next two transparencies on stabilization. And then we're coming to the main part of this lecture, and that will be reactors and how to apply this and how to characterize. So once again, this method you do not need to know by heart, but what we're now saying after this, the principles you should be aware of also for the lecture. Now, one point is how to make a carrier stable. Stable in view of energy input. I already told you have a sturdy carrier and you have hard collisions, then some of the carriers will break. This is not true if you have a packed bed reactor where the carriers are packed in a bed in a column, but it is true if we have a stirred tank reactor, or if we have a reactor, a bubble column reactor, anything like this. So the goal must be to stabilize this, and there's a technique developed by Marion Ansorge Schumacher from the Technical University Dresden, where she uses in the end a coating, a silicon coating. So silicon as soft material where the adsorbed proteins on the surface of the carrier get a silicon net thrown over. And this for one has two functions. For one, it retains the proteins from desorption by the silicon net. On the other hand, the surface gets a bit softer, and that prevents that the carriers are so easily breaking. And the result you can see here on the, so this is a carrier, a commercial carrier with an immobilized, with a lipase immobilized. So that's a carrier from Novozyme in Denmark, and it's a Candida Antarctica lipase B being which you commercially buy already ready immobilized. So you don't have to do anything, you just buy the carrier. And now what you can see is on the right side, you see how they look if you buy them. On the left side, you see if they are already diffracted. And so both now are being used for some time. And what you can see here, they're in a stirred tank reactor. And on the left side, you see the dark blue one is after 5 hours, and that's the number of particles with a specific diameter. So when you start up after 5 hours, the majority of the particles have a diameter of 500 micrometers. Now, if you stir this into a tank reactor with specific energy input after 30 hours, you can see this distribution of the particle sizes has significantly been changed. And so you already see it also optically. Now, if you make use of the silicon-coated particles, where we have this net for one preventing desorption, but that you can't see here. But if you look at the particle size, you see there's almost no significant change in the particle diameter. And so this is a very successful method that's also being used large scale. Now I see I've got a message in the chat. Left and right are switched. Oh yeah, sure. Wait a moment. No, it's right. Why do you think it shifts? On the right side, there are the particles which have the coating, and you don't see a change in the particle diameter. On the left, you see the diffract particle on top after 30 hours, and you see the broadness. But feel free to ask directly. Okay, maybe I told it in the wrong way. It might be that I switched between left and right when I was telling the story. Okay. I'll have to switch pointer to get the chat away. Yeah. Okay. Okay. So let's continue. Now, if we take a look at these carriers, so each individual white dot is here one immobilization carrier. The question is, where is now the enzyme? Well, we are not talking about snooker balls you're using for snooker, which are totally solid. We are talking about highly porous individual particles. So where a net of pores is running through the particles. And there's a classical study. Oh, one moment. I'm missing transparency. Where did it go? Ah, yeah, sorry. Somehow order was mixed. Okay. Now, if we're looking at this porous carrier, the Novozyme 435, that we just saw in the picture of the particles, and this is highly porous. Sorry?
We cannot see the slide. Or
the slide, okay. No.
Chatting with us.
Ah, that was because I closed the chat. Can you see it now?
Yeah.
Okay, yeah, thank you for letting me know. Sorry.
And I was reading what my colleague just wrote on the chat, and I think he's referring to the text on the previous slide, stearinity. Right. So stearinity would mean that those particles are not coated, right?
Yeah, so in the end, both experiments were started up, particles looking like this on the right side. Yeah. So totally true particles. And then in consequence, after stirring for 5 hours and 30 hours, so the dark blue or the violet curve, you can see that's a picture after 30 hours on top. You can see that on the left side, which is not coated particles, so the naked particles without any coating, just immobilized enzymes, they get diffracted. And so the particle distribution gets much broader. On the right side, we have the particles which are coated with silicon, and therefore after 30 hours, so the violet curve, you don't see a significant change.
Yeah, so probably he was referring to just the text.
Ah!
Take a look at
yeah.
the text.
Sorry, I was blind. I knew what I wanted to tell. Yeah, you're totally right. Okay, this I have to change right away. Yeah, thank you. One moment. Yeah, you're totally right. Stirring native is left, and So I'm using this transparency for I don't know how long. And you're totally right. Thank you for letting me know. So now we're back at the display, and now it should be right. Left native, right silicon coated. Yeah. Yeah, thank you very much. Very good. I'm sorry, I didn't understand the comment before because I didn't read my own text. Yeah, thank you. Later one. Yeah, so if we take a look at these normal lines commercial preparation, it's a highly porous carrier. But if we cut them and take a look at it with first hand spectroscopy, we can see that the relative enzyme concentration, the majority of the enzyme is just in the 100 micrometers, so we have a 500, 600 micrometer carrier, so half a millimeter in other words, that the majority of the protein is in the first 100 micrometers. Does anyone have an idea why not the total carrier is soaked with protein? Is immobilized protein? Yeah, right. So was Christoph is right in the chat is absolutely right. It's diffusion limitation. Because we have pores, and you see 100 to 150 nanometers in parts sometime. So the protein has to diffuse into the pore, and this is diffusion limitation, what we also have to fight in a moment for our whole reactor with, and that is the limitation overall. Yeah, now we're coming to the next round, and that's where do we apply those particles? So that's a major part of today's lecture. And so the easiest one is we have a packed bed, and this packed bed we can operate as fixed bed reactor, continuously flow through the reactor. Then we could have a fluidized bed reactor. That would be the situation where we have the hard collisions of the carrier systems. Or we can have the fixed bed reactor as CCR, the tank reactor, what we talked about, if we design this as a circulation loop reactor. Then we could just add them and have a slurry, plus the stir tank reactor. And you see some lectures booked just for completeness. Also, membrane retention is addressed as mobilization, but that's not what I share. I rather belong to the other group of people who say membrane filtration is no immobilization because we are not heterogenizing the particles. So the big difference is here we have a 3D reaction with no diffusion limitations, and all the four reactors on the left side exposit diffusion limitation. Now, if you compare the slurry reactor to the fixed bed reactor, there's a significant difference where we can already, without knowing anything, already assume we have a high diffusion limitation in this reactor. Why is this? Well, in the end, if you have one particle, which could be the dot of my laser pointer here, these particles are moving with the liquid if you turn stir. If you're now imagining this particle that's moving around here is a surfboard, and you're standing on the top of the surfboard, and if you're looking around you and you know all the water molecules by name, you will not see any different names because the water molecules will change with the same rate as the particle will change. To distract this a bit, you often insert some flow breakers here on the side, which introduce secondary flow, but that's not that efficient. If we are, in contrast to this, sit on a particle, my laser pointer dot here, the fixed bed reactor, at our surfboard again, then if we're looking around the surrounding, we see the other immobilized particles, but we will always, every minute, every second, see new solid molecules. And that is a big difference. And therefore, here with a fixed bed reactor, we're talking about convective flow. So we have a high convective flow, a high flow on surface of the particles. These are the classical concepts. And those are the ones that we had discussed in view of the different types of reactors where we've drawn the XY plots, so concentration time, concentration length, and so on. But 10 years back, a new company in Sweden came up with a different idea. These are rotating bed reactors. So here we have either a fixed bed or we have a rotating stirrer. They came up with the idea of rotating bed reactors. What those are, I will show you in a video. You can see right now, hopefully. A moment. Okay, so what is the principal idea? The company is named SpinChem, and it is the following. So we have a stirrer that is moving, you see, with particles, same rate. There we do have mass transfer limitation. So what can we optimize? The problem is reactants must be transported to the solid in order to react for sure. And now, where do we do the evolution from a stir tank to the fixed bed reactor? This magnetic stirring bar, in the end, is a hollow, a pipe. And if we stir the pipe, we can draw in, and if we have oil in the middle, we can draw in solvents from the middle, which will be pushed out to the outside. Now, if we would fill this tube with packed beds, in the end, we would have a stirrer that is stirring and then convectively installing a flow through the packed bed to the outside. And now if we transfer the stirrer to such a cylinder and we put in a filter and that the particles are not falling out, and we have an inner filter with holes with a tube sucking in the liquid. Then we put in the separation, we insert our particles. Then we get in a stir tank reactor, if we're replacing the stirrer with this device, a convective flow through a packed bed, which demonstrates, if we operate it continuously, a CSTR operation in contrast to a fixed bed, which is plug flow configuration. Yeah, and that would be the setup. And here once again, see the convective flow in the particles. Yeah, this can be scaled. If you're interested in this, you can take a look at this also in our labs. And I see Zeynep Persin is joining in here. She's student in my group. She's operating such reactors, for example. Okay, now you got to know now the principal reactors that there are, and we have already talked about the particles. And what we're doing the rest or the next half hour in this lecture is that we are thinking about how can we characterize now these particles or these immobilizates, so the active enzyme on the particle. Because the important point is that we design a process with the minimum reduced amount of diffusion limitation. Otherwise, we can have the best reactor if we have a strong with the best catalyst, highest activity. But if you have a high diffusion limitation, it will always be non-productive. So it's like if you're owning a nice Porsche, but a nice racing car, but however you're living in the boondocks outside on a farm and you just have dirt roads. So you have this nice car, but you cannot operate your racing car because you just have dirt roads around you and now no streets with tar, which are really soft, where you can drive at high speed. That would be the situation you would like to optimize. And therefore we need to know how dirty are the roads, how rough are the roads, and what can we do to get a soft road that we can operate our racing car. So that will be the next part of it. And the difficulty is we cannot take a picture and look at the picture and see, okay, that's a dirt road and that's a highway. We are blind, and so we need some methods to find out what we have ahead of us. Is this a dirt road or a highway? And that's what we're discussing in the following. So, for startup, theoretical considerations. We have for sure amount of available surface. Then we have diffusion limitation to consider. The surface overall we have in the carrier, what is also defined by the pore size and the amount of inner pore volume determining the inner pore size. And the pore size also has an effect on the mobility of the immobilized enzymes, namely how deep during the immolation process can the protein, the enzyme, penetrate the pores. So 3 fundamental rules. The pore size should be big enough to let enzyme enter, so pore size larger than enzyme size. Second, the pore size should be big enough that the enzyme has freedom of movement to change its conformation. So pore size should be at least, second rule of thumb, 3 times the main axis of the enzyme. And the third rule should be, or is, the pore size should be big enough that diffusion limitation can be mitigated. And this is always normally given as a pore size is 9 times the enzyme size. So these are some rules of thumb if you're selecting a carrier and you get from the different carrier supplier the information about the particle geometries. So this could be help in selecting. Yeah, and then we have 2 types of kinetics we can differentiate. These are the intrinsic kinetics. So new chemical bonds force modification on the performance of the enzyme compared to the soluble ones, or inherent kinetics that are influenced by the carrier materials modify the chemical microenvironment. So if you're immobilizing a protein on a highly charged surface area, the performance will be different to if you're immobilizing on a non-charged surface. Or let's assume we have a very hydrophilic surface, or we have a hydrophobic surface. It's a big difference. So in other terms, if we have a carrier which has a hydrophilic surface, so very polar hydrophilic, and we bring it into water, it will be nice distribute in our aqueous phase. But if you bring the same carrier to an organic solvent normally being hydrophobic, then our carriers will, which have a hydrophilic surface, will agglomerate to a big ball, and we have less surface area. So this is what comes into play modifying enzyme kinetics. Yeah, and this was just a picture of what I explained to you before, convective flow. We just already discussed this. And if we're looking on a particle, and here in the middle there's my laser pointer, that's the inner part, the gray area, that is the particle itself. And you're talking concentration, and then now you see a substrate concentration. And here in the outer far away from the particle, we have the bulk phase. B stands for bulk, liquid phase, where we have specific concentration. And then on the surface of the carrier, we always have this film boundary layer where the concentration is reduced. And then from the outside to the inside in the pores, we have diffusion limitation, and concentration is further reduced. We're not discussing this in detail because it's classical chemical reaction engineering, and you will for sure either have it already heard in pressure studies, or you will hear it in accompanying studies in your master. Now we're coming to the important point that for sure you need to know as principles, and that is how can we describe how effective now a preparation of biocatalyst is. And the question being behind this is how severe is diffusion limitation in contrast to the free enzyme being solubilized. However, it's not only diffusion limitation, it is also that maybe not appropriate surface charge like polarity, apolarity, hydrophobicity, hydrophilic character, hydrophobicity, so surface characteristics. And there, the first parameter that we introduce is the effectiveness factor. And how to study this? In the end, we plot Michaelis-Menten curve, that's substrate, that's reaction rate, as function of the substrate concentration. This is the Michaelis-Menten plot that you know for the free enzyme, so solubilized in the bulk phase. Now, if we introduce an immobilized enzyme that has a limitation in performance, for example, because of diffusion limitation, what is changing? Important point, in the kinetic plot, we will see a change that has become lower, but the association Km value will stick the same normally, and also Vmax will stay the same in most cases, but we need we have a slower broken order effectiveness, and so the calculation of this effectiveness factor, and this one based on kinetics, is termed the stationary effectiveness factor. It is comparing the rate at one defined substrate concentration between immobilized and non-immobilized, and the ratio between the rate of the free to the immobilized one, or in the first manner here, so immobilized rate of immobilized enzyme to the free one, that is a stationary effectiveness factor. So this is a very nice theoretical value. Work in industry, you don't have time. This would mean you need to carry out kinetic studies. Well, with the free enzyme still reasonable, with the immobilized one under repeatable conditions, that's already a harder one. So in the end, it's a nice theoretical factor, but you won't use it in industry. What you use in industry is a modified one. That's a so-named operational effectiveness factor. What does this mean? Well, you're running just a standard batch reaction, immobilized enzyme, and none with non-immobilized enzyme. So here you see the conversion plot for the free enzyme, conversion time. Then you determine the time that you need to reach 90% conversion, that's T90 value. And then you're repeating the same batch with your immobilized enzyme. And you will see if you have diffusion limitation, any kind of limitation, you will need more time to reach 90% conversion. So it's almost double here in this principal plot. And now the operational effectiveness factor compares the time needed to reach 90% conversion with the immobilized biocatalysis preparation in relation to the free one. And this you can use easily then either in lab scale, but also on scale. But you wouldn't do this on scale, you will do it in lab scale prior moving to on scale to find out if you compare different preparations, who has the shortest time or is most identical to the free enzyme. So that is the difference between stationary and operational effectiveness factors. But this is really a quick shot, and that is not good enough really to characterize what's going on if you want to scale a reactor, if you want to do detailed process layout. So we need to have some more detailed methods to do so. And there we are operating two different reactors to do so. And these we differentiate, we name one integral reactor, and the other system we name differential reactor. You already know both types of reactors. So this is a plug flow reactor, which is an integral reactor. What does this mean? Well, in the end, at the inlet, we have 100% starting material. At the outlet, hopefully, we have 0 starting material, 100% product. And over the length of the reactor, the product is being increased and the starting material is being decreased. So integral means it's accumulating the product from the inlet of this bed to the outlet of this packed bed. Integral, so integration, sum up of the product or consumed starting material. Now, you already know circulation reactor, CCR profile, plug flow profile, and as long as we have 20 times circulation flux in contrast to the resonance time flux. And now here we have a different situation. Why is the situation different? Because if we're not looking at the inlet of the overall reactor to the outlet, but if we're just looking at the fixed bed in the middle, then what enters here and exits here is different. And what enters here has a specific amount of concentration, and we might just add 2% of conversion from inlet to outlet, recycling it, and additionally add 2%. And that means differential reactor. So we only have a very small difference in conversion, and just by the number of the loops, we're coming to complete conversion under outflow condition to have our product coming to the outside. And this now has significant different effects in view of characterization. But prior to discussing this, now we are switching over and starting over today with Mentimeter again. What you can see here, so you go to the site menti.com, and the ID number for today is 10521526. So I'm just waiting for you to join in. Ten people have joined. How many are we now in the lecture? Okay, 32, 33, so I'm just waiting a moment. So we have 17. So we will, for the rest of the lecture, have some Mentimeter questions for understanding. So we have 19 people joining in. Bigger. 18. Okay, this seems also to be almost constant. Half the people have joined. So I'm starting over. So first question, what type of reactor does the differential reactor resemble? Is this a plug flow reactor, fat batch, or CSTR? What do you think? Yeah, it's a CSTR. That's what we just discussed. We have discussed several times in the lecture. So those who have answered plug flow reactor or fat batch, please talk to your colleagues. There are enough who have understood it. The circulation reactor, if you have larger than, sorry, I have to switch back. If you have a circulation reactor and you have, that's a differential reactor, and that you have larger 20 times the circulation rate than the resonance time flux, then you're in the CCR profile. Okay, so let's take a look at the leaderboard, and more questions to come soon. And so now the leaders are Dobby, S, Henry, Lola, VoteGoat, Katie, Jimbo, etc. Okay, going back to our lecture. So to note, in contrast to the integral reactor, only a short packed bed is needed because of the high recycle stream. And this is now an important rule of thumb. So we had defined 2 lectures before in the CSTR. We do have a higher enzyme consumption. But if we take a look at the differential reactor, here to the integral, compare this to the integral reactor. Here in the integral reactor, we have to make sure that from the inlet to the outlet, we get 100% conversion. Meaning, we have here a high investment of enzyme activity. Since in the differential reactor, we are always circulating in the loop, we can have less investment of biocatalyst because we just do one more cycle to make use of the activity. So that's the difference there. And at the end of the day, for a new process, besides the properties of a CSTR to a PFR and from a reaction engineering point of view, it is also an economic decision you have to take to select. Okay, now we're starting up for this characterization method, making use of the left side with the integral reactor, and I'm letting you know when we're switching over to the differential reactor. Now, what we're doing, what are we doing to characterize? And this is now important because these principles you should know by heart. We're in principle operating two packed bed reactors, left side and right side. The difference of these two packed bed reactors is the bed volume. So on the left side, we have a very small volume V1 of packed bed, let's say it's 2 centimeter high. And on the right side, we have a big volume of packed bed immobilized catalyst. Let's say it's 4 centimeters, so double size. Now, if we want to see if we can measure any diffusion limitation, we now would like to operate both reactors with same residence time. Same residence time, since residence time is a quotient of volume divided by flux. Meaning, if we have a smaller volume, we have a lower flux. If we have a larger volume on the right side, we need a higher flux. And if the ratio is the same, that is the residence time, and the residence time is constant, we can establish a situation where we have the same residence times, left and right. But on the right side, we have a much bigger reaction volume, or in other terms, packed bed situation. So anyone, any questions to this point? Because this you need to have understood, otherwise you're lost in a moment. Okay, I don't see any questions. Okay, then let's go ahead. Now we are doing experiments in both reactors at the same residence time. And what we're doing is, in the outlet, we're going to measure at the moment the conversion. Yeah? We're running it for some specific time, and we're measuring in the outlet the conversion. This will be one operation point. Okay, so at a defined flux F1, we measure one conversion here. At a defined other flux here on the right side, we're measuring conversion point here. So F2 is the one with the high volume, F1 with the low volume, both at the same residence time. Okay. Now, these results of this experiment we'll plot in a plot where we have on the y-axis the conversion, and on the x-axis we have the flux. And here we just have two data points right now, which at the end of the day, will give a curve of the left reactor, F1, F2 in the right reactor. So left F1 was small volume, right reactor F2 was big volume, double size. Okay. Now I don't tell you the answer. We will switch over to Mentimeter. What you have to think about now, and what is the question in the Mentimeter being asked to you? What is the course that you are expecting here? So, and conversion is defined as we have defined it so far. So starting material minus extra concentration divided by the concentration of the starting material. Okay, switching over to Mentimeter now. Just waiting for you to join in. '17. Okay, we just have a limited number today in the millimeter. Okay, but it's 17, 18, that seems to be stable there. Yeah, so then I will start the millimeter. You see now here three curves, A, B, C. A, B, and C. What would be the course under ideal conditions where the volume is constant? So we have in F1 the slow volume, slow flux, and with the high flux F2 we have appropriate high volume, we have equal residence time. What would be the course now you're expecting in this plot? Will this be A, from 0 increasing the conversion with higher flux, or will it be B, no change at all, or will it be decreasing under ideal conditions? So no negative effect under ideal conditions. Oh, that's a broad distribution. So B is the right answer, and B was constant. We will discuss this in a moment. Let's take a look at the leaderboard, which has changed. Oh, I'm happy to see that I'm successful again. Yeah, Bedent, Earth, Dobby, Jembo, Brandbrook. Oh, I don't know Brandbrook. Must be something exciting. Yeah, so let's switch back to our transparencies and I try to explain. So, back to our layout. So, we have same residence time, we have small bed volume left, appropriate relative small flux, right? High volume, high flux, delivering same residence time. If we do not observe any diffusion limitation, since we have the same residence time in both reactors, ideally we should have the same conversion, because residence time will be the available amount of catalytic activity will deliver the same conversion. And therefore, if we plot this, that's a reaction control. So the flux change at same resonance time will not have an effect on the conversion. But now, if we are unlucky, and that's what we like to find out, is that we have a diffusion limitation. And in other terms, then the picture looks like this. Meaning at low flux, we have lower conversion than at the high flux. Why is this? Well, if we have the same residence time, which under ideal conditions delivers same conversion, this will be changed if we have diffusion limitation. Now, if we have diffusion limitation, meaning, a moment, just going back here, this boundary layer, so the gray dot here, that was our particle, and on top of the particle we have this boundary film layer. And now this film layer depends on the flux, the convective flux going along, and the convective flux also determines a bit of penetration into the carrier. Diffusion limitation means that we have a high film layer here, and you see here the concentration is decreasing further inside the particle. Now, if this particle is moving as to a tank reactor, where we said we are on the surfboard and just serving with the same liquid molecules in this tank reactor, then the height of this film layer will not be influenced. But if we are in a packed bed reactor where the particle is fixed and the liquid is constantly passing on top of the surface, we always see new particles, liquid particles, solvent particles here, then this diffusion layer is reduced. And that is the trick of this experiment. So if you're going back to the experiment, in both columns we had the same resonance time, we have different volumes and different fluxes. The different fluxes do not have an effect if we have ideal conditions. But if you have a diffusion limitation, even delivering the same resonance times, the absolute convective flow on surface of an individual particle here in volume 2, the flux on the surface is much higher because flux 2 is much higher. So if we are limited by diffusion because of the film layer, here the film layer in the right column will be smaller than the left column where we have lower flux. Less exchange on surface of the particles in the film of the solvent molecules. Therefore, we have here in the right side higher flux, lower diffusion limitation, and in consequence, that is the result that we see here. We see an increase in conversion because of diffusion control. So diffusion limitation is given if conversion increases with flow rate, limitation by mass transport. So that is the result, what we just discussed. Any questions so far? Okay, I don't see any. So I hope you have understood this. Now we're doing the same practice again and we can see if you have understood it. Now we have the same 2 Coulomb reactors, but now we run the experiment a bit different. Or no, we're running the experiment the same, but we're analyzing in a different manners. So once again, on the left side, we do have the small packed bed. On the right side, we have the large high packed bed. Volume 1 is smaller than volume 2. Now the trick is, what we're going to do is we generate different residence times in both reactors. So we run in both reactors, we install not only one residence time, and we're just looking at the flux change. Now in the left reactor as well as in the right reactor, we're installing, let's say, 10 different residence times, 10 different fluxes, but identical left and right. So in principle, similar performance. And then we're plotting now not the conversion as function of the flux, we're plotting conversion as function of the residence time. Now what we're expecting here, we will take a look first at the Mentimeter and then talking about afterwards what we have seen. So you can join into the Mentimeter. I'm just waiting for a moment. So 17, 18. Okay, it seems to be the number. So question comes. What would be the course under ideal conditions if we now plot conversion as function of the residence time? Once again, you can choose between A, B, and C. Ideal conditions, what would you expect? Sorry, and tau constant is wrong there. We have alternating tau is copy paste error in the question. Okay, everyone said A. And no, I forgot what was A. I don't see it anymore right now here. Okay, we will see in a moment. So let's take a look at the leaderboard and I will explain in a moment. Okay, this has changed a bit. So I've lost. Leaders are Willem, Dobby, Brandbroken, Henry, Vote Heartstorm, and so on. Okay, let's take a look what reasons. So we can differentiate reaction control and diffusion control. Reaction control, yeah, you're plotting both reactors. So the small volume are the red dots, the big volume are the blue dots. So, and the small dots, so the volume 1 is smaller than volume 2. Residence time defined as a quotient of volume and flux. And now, under ideal conditions, what would be reaction control? It will look like that conversion will be increasing with residence time. That was A before, because that is what we're expecting, that the course of a typical, like in a batch where you have normal time, and the residence time is nothing more than the reaction time given to reach a specific conversion. If there's no difference in performance, no diffusion limitation, so both reactors will be on one line. Now, if we have a diffusion control, meaning that with diffusion limitation in the carriers, we once again see the difference between short bed, low flux at the given residence time to large bed, high flux at a given residence time. And in consequence, if we have for reactor 1 this performance, reactor 2 will be much better in terms of conversion as function of residence time, because we do have, as discussed in the example before, a much higher flux, resulting in a much higher conversion because of reduction of the film layer, reducing the effect of diffusion. So, to note, mass transport limitation, conversion increases with higher flow rate. Next important principle. Yeah, then we still have to consider that at the end of the day, we also have a further effect, and that is a pressure drop. So let's assume you have your column, and you can see now my picture. Let's assume we have a column, that's my mark, yeah, and we're packing this mark with particles, and we have a flux in from the bottom and flux out on the top. And now once you would pack in here large particles, balls of like clay balls for children use, or a centimeter, or we put in there, let's say, peppercorns. So we have particles with a large diameter in this container, in this packed bed, or small diameter. Now, if we pump into this reactor, the force that we need to move the liquid through this packed bed will be different if we have large particles or if we have small particles. And that is what we're naming pressure drop, because if we need to invest a high force, a high flux, a high pressure to pump the same flux through this packed bed, that's pressure drop from inlet to outlet. If we have a high flux, there will be a high pressure drop from the beginning to the end. And this is important because if we not have on my mug here, but if we're now in industry and we have a 2 meter, 3 meter high column, that's some kind of height, and some pressure could be built up, and in consequence, the material and our plant must be stable against this resulting pressure. And typical values you can see here. Here's a pressure drop in the packed bed, depending on particle size, and you can see the smaller the particle, the higher the pressure drop over the height of this packed bed. Now, one point is, the smaller the particles, the higher the surface, the more enzyme we can mobilize and we can bring into the reactor. On the other hand, the smaller the particles, the higher the pressure difference between inlet and outlet, the pressure drop in the resulting packed bed reactor. So at the end of the day, you have to find a compromise between surface area directly related to activity that you bring into the volume to the pressure drop, the pressure on your reactor system, and so that's an economic, but also a plant operation point, depending on what is your equipment on the site where you want to run the operation. And this brings us to the question, what is the largest possible diameter we can apply there? So, determination of largest possible particle diameter. So, there's some, once again, rule of thumbs. So, in a plug flow packed bed reactor, normally you're operating with particles from 200 to 400 micrometers to ensure low back pressures, so pressure drop in the column, but large enough to have a high amount of biocatalyst to be immobilized and brought into reaction volume. In a stirred tank reactor, so there we're standing on your surfboard and are moving with the particles with the stirrer speed, there you always normally use very small particles because there the diffusion limitation, as already discussed today, is much higher. Therefore, we want to have the smallest particle possible, ideally, that we can still separate by filtration afterwards. So microfiltration that we use for sterilization is often 2 micrometers to 0.2 micrometers in that range. And so we are using particles around 10 micrometers. We can still filter them off for one. On the other hand, they are small enough that we can cope with some of the diffusion limitation. Now, what's the experiment that we can find out practically what would be the best particle diameter that we are applying in our reactor, in our plant? And here we are now switching over from what I introduced beforehand, from the integral reactor to a differential operated reactor, so circulation loop reactor, what we discussed just before to determine the lowest possible for diffusion. How does the experiment run? So determine largest possible diameter. We can use the big particles we have here, which we then ground to different sizes. And so in solid process engineering, this is named classation. So you have different filters with different pore sizes. And now if you rinse particles, you can filter off different particle sizes by the net hole size of this stainless steel filters. So they get different fractions of different sizes of particles. Now, you always pick one size of this particle in such a differentially operated circulation loop reactor. And then you determine the initial rate in this reactor of the performance of the particle. Initial rate is easy because, you know, in the differential reactor, we just have 2 to 3% conversion per pass to the packed bed. And if you remember the section on kinetic studies, we said you're in the initial rate measurement region if you're below 5% conversion. Therefore, overall conversion is not to be allowed to be exceeding 5%. And with this, we can run initial rate measurements in the continuously operated stirred tank reactor under flux condition and determine V0 dependent on the particle size we've inserted here. We run with 5 different particles, we establish 5 constant operation points, and then we can plot the starter. And now we plot the particle diameter. Now let's say we had these 5 diameters in the differential rate reactor. And then once again, we define the effectiveness factor, but this is now different to the stationary operational effectiveness factor. This was stationary effectiveness factor was in relation to kinetics, if you remember. Operational effectiveness factor was in relation to time needed to reach 90% conversion. And now we have here the effectiveness factor in view of the particle diameter, which correlates the initial rate of a particle diameter we're analyzing right now to the initial rate of the smallest particle diameter we have analyzed in our series. And if we are plotting this, then if we do not have any effect, so no diffusion limitation at all, then the particle diameter should not have any effect on the performance. So the effectiveness factor should always be 1. But if we do have diffusion limitation in the differentially operated reactor, then we see a clear decrease in the effectiveness factor with increasing particle diameter in the plot. So once again, also quick experiment you can run in the afternoon if you want to find out what's going on with the charge of mobilizate you bought from a supplier for your plant, and you don't need so many points, just 3 points will do. And that's up here is the particle diameter you have bought, and now you grind it and just see that you have almost equals particle diameter fractions in view of size with those one reactor, and then you see do I see a difference or no, and then you know if you need to buy or modify the particle diameter. Last point, last experiment we're running through, that is determination of pore diffusion limitation. And there we also make use of the different reactors. So far we're looking at the particle and the film layer and to see what's happening there. Now we're looking inside of the particle, the pore diffusion. So this experiment is similar to, or a little bit similar to what we've done before. So we're using the differential reactor again. We have now a constant residence time. Constant residence time means the inlet pump here ahead of the reactor, we do not change. It's constant in flux. So the overall residence time is the same. Now, what is the trick in this experiment? The trick is that we are operating the circulation pump, what you see here, at different rates. So let's say we start with one rate, we wait for a steady state, what we see at the outlet here, constant conversion, and then we're increasing the pump rate by factor 2, for example. And again, so we're increasing the circulation rate. And what do we see? Well, you can already imagine if we do not have any pore diffusion, then the conversion should always be constant, because the residence time pump here at the inlet determines the residence time in the circulation loop, and this should not be affected by the circulation. But now, if the particles that we have in this packed bed, and they have a defined pore size, and if we have a diffusion limitation to the pores, we would expect the higher the flux in the cycle, the better the pores are penetrated. And we have a higher flux through the pores, reducing pore diffusion. And then the conversion at the outlet will not be determined on the inlet flux by the inlet pump. It will be determined by the circulation loop flux set up by the circulation loop pump. That's a trick. Okay, just described here. And we can then, because of CSTR operation, differential reactor, we can plot the reaction rate, and we can see this in view of, depending if we have a large Reynolds number or small Reynolds number. So the Reynolds number is a dimensionless number, as you might you will remember from bachelor studies. It's now taught in bachelor studies. The higher the Reynolds number, the higher the turbulence in the system is. The smaller the Reynolds number, the smaller the turbulence, and depending on our system setup, we can once again also differentiate here. But the principle is as explained explained before. So the higher the flux in the circulation loop, the higher penetration flux to the pores we have. If we have a pore diffusion limitation, this will be directly seen in the final conversion at constant residence time in the overall system. Yeah, and with this, we are at the end of immobilization, and we have 10 minutes left over in the lecture today. And somehow I left out one multimedia question, so I will just switch over to the multimedia. Let's see. I forgot. Just waiting for you to join in. Okay, 19. So last question. Yeah, this comes back to last lecture. What is this challenge if you're working in a packed bed reactor with this reaction? What do you think? And just repetition from yesterday. What could be the challenge if you're working in those reactors we're just talking about with this reaction system we already talked about yesterday? Unstable residence time, fast enzyme deactivation, or back reaction, low conversion. Okay, 10 seconds to go. No, okay. So unstable residence time was the right answer. Fast enzyme deactivation was wrong. You don't know by the reaction scheme. Back reaction, low conversion, we also don't know. You always have to see what is the trigger point in view of the principles we discussed. And the co-reaction product was example. You can look at it. We had it yesterday, noontime. And actually, you can see it in the video there, the answer. If you see a gas compound that's being produced, and here it was carbon dioxide, because it was the use of a decarboxylase, then you can already assume that in a worse manner, you have unstable residence time because of forming a gas phase, reducing the liquid reaction volume and changing the residence time in the reactor system, like what we discussed just today as well. Yeah, so take a last look at the leaderboard. Yeah, and the winners are overall from today's session: Dobby, Vedant, Halfstorm, Katie, Earth, Simba, Lucy, Bram the Broken, and so on. And Lisa has lost, I see. Okay. Good. Last minutes, very shortly, membranes. You know, cherries. And sun, getting warm, it's raining, and the cherries become big, and at some time point they explode. The fundamental knowledge there is that we have on the outside of the cherry a selective membrane. Inside we have a high carbohydrate sugar concentration. Outside the rain is sugar free. So we have a concentration difference outside of the membrane to inside. Now this is driving force that we have a water flux from the outside of the membrane to the inside to equilibrate, to reduce the concentration in there. And that is the reason why summertime sun, rain, cherries explode, because we have too much water being transported inside. What should be the message of these examples? They are selective membranes, and that's true for the cherry, because I haven't seen any time in my life a cherry that is leaking water. So water transport is just in one direction. And that is because of this osmotic pressure, because of the concentration difference. Okay, Those are membranes. And this is what we're using, large scale or small scale. And we're differentiating 5 different membrane processes. Classical filtration, that's the one I just used this morning ahead of the lecture, where I was filtering my coffee to extract my coffee for my coffee mug that's empty now. Then we have microfiltration, that's between 10 and 0.1, 0.2 micrometers. That was also often named sterile filtration. With this I can retain yeast cells, small cells. Then we have ultrafiltration. Ultrafiltration still has pores in the membrane, but it is filtering, it is retaining solubilized compounds. So with ultrafiltration, we do not have a suspension where we're solid and liquid. We have macromolecules in liquid that we are retaining with the membrane. Then below this, we have nanofiltration. In nanofiltration, we often have no pores anymore. Sometimes we have pores, but often we even don't have any pores anymore, but we have a diffusion through the membrane material, and the lowest error is reverse osmosis. Let's take a look at ultrafiltration. That's what we're using, large scale or small scale also, to retain homogeneously solubilized proteins in liquid. So to recycle enzymes, for example, in a stir tank reactor, in an enzyme membrane reactor. Here you see the same scale on the x-axis, but now with different kind of sizes of components. And we've seen ultrafiltration runs from 0.1 to 0.01. So this is this range here. And there you can see we can retain viruses, we can retain proteins, soot, tobacco smoke, gelatin. The bigger the particles, we are in a suspension area like bacteria and yeast cells. That would be typical tasks for microfiltration. Now, the big challenge is in membrane filtration that we do not have all the pores with a total identical diameter. And that is the challenge if we're selecting membranes for our processes, because we always have a distribution in the pore size, what you see here. And this has a direct effect on retention. Retention means how much of the homogeneously solubilized protein is retained by the membranes, and how much of the protein do we lose by a small fraction of larger pores. With a protein, it's easy, because a protein is just like if you have wool, so it's just bound together to a big molecule, and that is stabilized and being retained and has a specific hydrogen volume. If you're retaining polymers like polyethylene or any polylactic acid, something like this. So if we have one string as a polymer, then story looks a bit different, because these have no interactions in the chain. So we just have one string, and it's like if you're sewing any clothes or so, and you have the needle. If one end once enters the hole in the needle, so if one end of the polymer, of a linear polymer, one enters the hole in the membrane, it's lost, because it will just run through. That's the difference to proteins, which have 3 and quaternary structures, which are stabilized, and you cannot unfold it that easily to just one string. Yeah, and because of this, you can see that if we have a specific molecular weight here on the x-axis, we have resulting a specific rejection, and this rejection is how much is retained. And let's assume we have the supplier, we order an ultrafiltration membrane, says a molecular weight cutoff is 60,000 Dalton or 60,000 grams per mole, which would be, for example, here. This is normally giving as a 90% or 95% retention, meaning you have some compounds which will be totally retained, but you will have other ones which is not retained, and you lose this. And this is one point we will discuss next lecture. So next lecture for startup, we still have 10 minutes to sum up filtration, membrane filtration, and then we go into case studies and practice for the examination. Yeah, with this, we're at the end of today's lecture. I thank you once again for joining in. If you have any questions, sum them up for next time, especially for the next lecture, Biocatalysis, enzyme technology. For both lectures, that we have some more time to discuss your questions next week. And stay healthy and see you online next week again. Bye-bye.
Bye-bye. Thank you.
Thanks so much. Bye-bye.
Thank you.